So in this last part of the course, what we've been focusing on, in some sense, are generalizations of the fundamental theorem of calculus. And you've seen it come up again and again. And so what is the idea of the fundamental theorem of calculus? It says, if I want to know something about what's happening on the interior, I can look at an antiderivative on the boundary. So this one, the conservative line integral, says, suppose I'm integrating along a curve, gradient of f ds. Remember, the gradient acts a lot like the derivative does. What does it do? Well, it says look at the function at your endpoint minus the function at your start point. In Green's theorem, we say, okay, well, suppose I want to know the integral over the region of some expression n sub x minus m sub y. Notice these are derivatives. And that says it's equal to the integral on the boundary of our region, m dx plus n dy. So again, if you start here and compare it to there, it's like you've taken derivatives. And you can take Green's theorem up into 3 dimensions. You can do it in sort of the straightforward adaptation, which is to say, well, suppose you have a surface, and you have a surface with a boundary. Say, well, the integral along the boundary of that surface of f dot t ds, well, I have to do something that's the derivative of f. In this case, it's the curl. That's del cross f. Or you can do sort of the analogy and say, okay, what about if we think about Green's theorem in terms of flow? Well, we can do that too. Suppose you have a solid. And I say, well, I can integrate on the bounding surface of that solid f dot n, which is the flow through the surface. That's going to agree with the integral over the whole solid of the divergence of f. And again, the divergence is like a derivative. Now, this idea is actually a really important idea in mathematics, and you can see this if you go further on in mathematics. But for now, we have to stop here because we're out of time. This is the end. Now, one of the things that's good to know is how do you spot these things in the wild? So it's like, sure, I know I need to know these types of problems, but how do I know when I encounter them? Well, there's a couple of things to look for. If you see a curve, which you start and end at different points, well, the only place where you have a curve that starts and ends at different points is in this situation here. So look to see if it's a conservative line integral. It will not always be conservative because not everything is the gradient of something. So in some sense, single variable calculus was really special in that everything that we encountered was basically the derivative of something, even if we couldn't find it. But not the case when you get to vector calculus. Well, maybe it's a closed curve. Well, if it's a closed curve in the plane, and when we talk about the plane, we really mean the xy plane. Closed curve in the plane, that's Green's theorem. Or maybe you're like, well, I have a region, and I want to know the flux through that region. That's Green's theorem. What if it's a closed curve in space? So it's not in the xy plane. Well, if it's a closed curve in space, you do the generalization of Green's theorem, which is Stokes' theorem. Maybe you see something that has the word curl. Well, if you see curl, think Stokes, because Stokes is the part that had the curl in it. Maybe you have a surface, and that's the surface with an edge, surface with a boundary. Again, that's Stokes' theorem. How about divergence? We'll look for keywords. A solid. So the only thing that's a solid, a 3-dimensional integral, shows up in the divergence theorem. So notice you can count the number of integrals. That tells you the type of thing. You're either a 1-dimensional integral, or you're a 2-dimensional integral, or you're a 3-dimensional integral. So the only time a 3-dimensional integral showed up was in Gauss's divergence theorem. So if you have something that says the word solid, think divergence. Maybe you have flux through a solid. That's a divergence. So think about these words. If you see the word flux, you say, okay, is it 2-dimensional or 3-dimensional? And depending upon which case it is, you react appropriately. What if it's a closed surface? Now, what does that mean? It's because you have two types of surfaces. One is a surface with a boundary, and one is what we call a closed surface, and really that means a surface without a boundary. So an example of the distinction would be a surface with a boundary. That could be like a hemisphere. So they take the top half of a sphere, Well, there's the equator. That's the boundary. But a closed surface would be if you took the whole sphere. Well, there's no boundary because it just continues on and it wraps back in on itself. So one thing to keep in mind when you're doing these problems, and for me, this is what makes things fun, is if you have a line integral or Stokes' theorem, you can always change your curve or your surface to fit the boundary. As I like to say, this is your BYOS. Bring your own surface. And that's a good tool. And that's a technique you can use to make a lot of Stokes theorem problems a lot simpler. So since this is our last time, our last hurrah, we just want to do a lot more practice, and we're really going to be focusing on Stokes and Divergence. And we're not going to usually say which one it is. We'll try to pick up on clues. Of course, one of the clues might be use the divergence theorem, but maybe they're not going to all be that clear. So let us begin. So let T be the solid consisting of points x squared plus y squared plus z squared less than or equal to 4 and z greater than or equal to 0. Let boundary of T, so remember that this partial symbol, that indicates boundary. It's the bounding surface of T with outward pointing normal vector n. It occurs to me that you might not think that's a T. That looks a lot like a J as well. That's just a fancy curly T. And what's the problem? Well, find the integral on the boundary of T of this expression dot n dsa. Now, what problem are we in? What are our keywords? Well, here's our big keyword. It's a solid. So when we see the word solid, we think divergence. And in fact, that's what's happening here. Because if you think about what this expression is, what we have here is that this is the integral over our boundary of f dot n dsa. So this is computing the flux, or the flow, of the function capital F, the vector field of F. All right, so this is a flux through a surface, and the surface is that of a solid. So this one is going to be a divergence. All right. Now let's get a handle on what's happening here. So T is our solid. Well, what's our solid look like? X squared plus y squared plus z squared less than or equal to 4. That would be a sphere of radius 2. Z greater than or equal to 0 means we're over the xy plane. So we take our x squared plus y squared plus z squared less than or equal to 4 and just cut it in half at the xy plane. And so we get our hemisphere. So this is a hemisphere of radius 2. Now, we might switch to spherical coordinates if we have to. But let's see if we have to. Let's find out what we're trying to do. So according to the divergence theorem, this is going to be the triple integral over our whole solid of the divergence of f. So we're going to take f, and we go through each expression and take the derivative. Now, there should be some clues, by the way. We don't want to do the integral that was given to us. When you see expressions like y plus 1 to the z, that's sort of like, why would we ever do that? And the answer is we would never do that, because we're going to find something that lets us get rid of these expressions. So we go through and we take our derivative. So let's see what we have. We take the derivative here with respect to x, and again, this term will disappear because there is no x. So we get 5x squared. Here, if we take derivative with respect to y, well, we get 5z squared plus e to the y, and then that term goes away. And then over here we get derivative with respect to z, that's 5y squared minus e to the y. All right, so that's not so bad, and we have to do this dv. So good news, we get a little bit of cancellation, just enough. All right, so that's gone. And so we need to do something. This is a non-trivial integral. So we probably do want to switch now to spherical coordinates. Let's take a look at what we have on the inside here. This is really what's left is 5 times x squared plus y squared plus z squared, which of course In spherical coordinates, 5 becomes 5. No surprise there. But x squared plus y squared plus z squared becomes rho squared. All right, that's a nice function. How do we describe the hemisphere of radius 2? Well, because it's perfectly rotationally symmetric around the z-axis, so in other words, we get the same shape as we spin, that tells us that theta goes between 0 and 2 pi. For our phi equals 0, that's straight up, and that's hitting the surface. In fact, we keep hitting the surface until we hit the xy plane. And that's phi equals pi halves. So 0 less than or equal to phi less than or equal to pi halves. And r goes from the center, sorry, not r, rho goes from the center out until we hit the sphere. And the sphere is radius 2. So 0 less than or equal to rho less than or equal to 2. So these are nice bounds. In fact, it's a spherical coordinates. You should expect something that looks like a part of a sphere to have nice bounds. So integral, integral, integral. This will be 5 rho squared. Then you get our rho sine of phi d rho d phi d theta. Remember, that's our dv. And our bounds, 0 to 2 pi for theta, 0 to pi over 2 for phi, and 0 to 2 for rho. Well, we can split these up because these are nice bounds. So really we can split this up into 3 integrals. 0 to 2 pi for theta, 0 to pi over 2 for sine of phi d phi, and 0 to 2 for 5 rho to the 4th d rho. First integral, 2 pi. That's not so bad. Second integral, actually it's not so bad either. The integral of sine is negative cosine. And then you're going to evaluate from 0 to pi over 2. But when you plug in pi over 2, you get 0. Cosine of pi over 2 is 0. So you get 0 minus 1, because cosine of 0 is 1, which means this becomes 1. And now, this last part, well, easy integral. Rho to the 5th. And then we're going to go from 0 to 2, which means we get 2 to the 5th, or 32, giving us our final answer of 64 pi. And that's our divergence. That's it. We're done. Ah, nice, nice. Okay, so that one's not so bad. Let's try another one. So, let T be the solid given by 1 less than or equal to x squared plus y squared plus z squared less than or equal to 4, and z greater than and equal to 0. And let F equal 2xz plus e to the yzi plus arctangent xz squared plus yzj plus x minus z squared k. Use the divergence theorem to find the integral on G, f dot n d sigma, where G is the surface of T and n is the outward normal vector of the surface. Now, you might say, what's the clue? Well, there's a big clue right here. Divergence theorem. That's a really big clue. That's really hard to miss that one. If you did miss it, there's some other things. There's the word solid. All right. There's also the fact of what we're integrating. See, we're integrating f dot n, d sigma. Now, if this were to be a Stokes theorem, we'd have to make sure that we are integrating curl of f dot n. And so if you're just integrating f, unless it's miraculously a curl of something, forget it. Hopeless. Hopeless. So when you see an f dot n on a surface, that's a clue, again, that we're doing something that's going to be a divergence theorem. Now let's see if we can understand what our solid is. So let's get a handle on it. So this is T. Now it's not quite so fancy a T. X squared plus y squared plus z squared. And when we see that, we think of sphere. So what we have is we're going between a sphere of radius 1 and a sphere of radius 4. So, and again, z greater than or equal to 0 says it's the top part. So what we're starting with is we're starting with sort of a small sphere of radius 1, and only the top part of that. And then there's a larger sphere of radius 2 that we're inside. So again, we're just cutting off the bubble. So it's like we took a hemisphere, but we scooped it out. If you will, it's like a cantaloupe. If you ever like cut a cantaloupe in half and scooped out the middle seeds, then that's what you have, this nice fleshy part, the deliciousness to work with. Now, well, let's find out what the integral is. Sometimes, once you just know the integral, you don't even have to do much work. So, we're going to do divergence theorem. So we get that this integral on our surface, f dot n d sigma, which, by the way, in case you're wondering what's this d sigma notation, d sigma is another convention that some books use. It's what we've been calling dSA. Why did they use sigma? Well, they needed something, and they thought SA was too long to write out. So that's equal to the triple integral over the whole solid of the divergence of f dv. So we got to compute this divergence. So triple integral, well, go through term by term. Get rid of the first term with respect to x. The nice thing is that this e to the yz goes away, and we're going to get 2z. Go to the second term. Take the derivative with respect to y. The arctangent, the one that looks intimidating, gone. And we're just left with a single plus z. And we go to our last term and take the derivative with respect to z. And we're going to get a minus 2z. And that's our integral. Well, the 2z and the minus 2z cancel. So this becomes the integral over t of z dv. All right. So now we know what we're trying to integrate. All right, but this is a non-trivial integral. If it had just been the integral of 1, life is good, and we'd be almost done. But that's all right. We don't mind doing the work. So what do we need to do? Well, we think about our bounds. A lot of the bounds are going to be the same. Again, that rotational symmetry all the way around the z-axis tells us that theta is going to go between 0 and 2 pi. And for phi, well, phi equals 0 points straight up, and we're going to go all the way until we hit the z equals 0. So again, phi goes from 0 to pi over 2. And now about rho. Well, rho we always think of as coming out from the center. So here's our center. And we come out until we hit. And what do we hit? We hit the inner bubble. And then we keep going until we hit again. What do we hit there? We hit the outer bubble. So what we get is that rho is going to go in between these two spheres, one of radius 1 and one of radius 2. So those are our bounds. Now the other thing we have to do is to think about what happens. Z. Well, what does z become? Well, z is rho cosine phi. Okay, so that's what we have. And so what do? Well, so this is going to become integral, 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 rho cosine phi, then our dv, rho sine of phi, d rho d phi d theta. Theta goes 0 to 2 pi. Phi goes 0 to pi over 2. And rho goes 1 to 2. Again, we can do something like what we just did, which is we can break things up. So we get 0 to 2 pi of d theta. We get 0 to pi over 2 of cosine phi, sine phi, sine phi, d phi, and integral 1 to 2 of rho cubed, d rho. The first integral is 2 pi. Now the second integral, you have a whole bunch of things you can do. You can do a double angle and say, oh, this is like of 1/2 sine 2 phi, and then you can integrate that and get 1/4 cosine 2 phi, or negative 1/4 cosine 2 phi. Or you can do a substitution. And let's just do that in our head. So if we let u equal sine phi, and I know that doesn't look like a sine, but that was a sine, then that's our du. So it's really like a u du, which means that the integral of this would be 1/2 u squared. And then we're going to evaluate 0 to pi over 2. And if we evaluate, what do we get? Well, plug in pi halves, you end up with 1/2. And that's it. That's what you get. Okay, nice. That's a clean answer. And we like it when we get a nice answer. Okay, well, last one. All right. What's that? Well, the integral here, that's rho cubed, so we're going to get 1/4 rho to the 4th. Evaluate 1 to 2. Well, that's 1/4 times 2 to the 4th, which is 16, minus 1 to the 4th, minus 1. Or if you like, 15/4. Okay, so what do we have? Well, the 2 pi and a half. Is it really a half? Yeah, that seems right. Okay, all right, sorry. I shouldn't doubt. That sounds terrible. It's always good to check your work. 2 pi times a half is pi, times that by 15/4, so we end up with 15/4 pi. And that's it. We're done. Okay, so see, really it's not such a bad technique or bad problem. What do you need to do? You need to say, well, all right, I need to recognize this is a divergence theorem. I need to do the divergence, set up the integral, be prepared. It might be something which is a different coordinate system. In fact, it often is. And the reason it often is because it turns out that it's hard to describe things in coordinates. If you're, say, in rectangular coordinates, you tend to get things which are boxes, which are not very interesting surfaces. But in spherical coordinates, you can get things which look like spheres, which are more interesting. And we like things which are more interesting. It's just sort of a natural tendency. Okay, well, let's keep going. Let T be the solid. Oh my gosh. Ha ha ha. Right away. They're dropping hints. It's a solid. It's given by square root of x squared plus y squared is less than or equal to z is less than or equal to 2 minus quantity x squared plus y squared. And we have our function f, which looks terrible. And it's like, we don't want to integrate that. Well, let's find out if we have to. Use the divergence theorem. Okay, that's a pretty big clue that we're going to use the divergence theorem to find integral f dot n d sigma. All right, so this is very, very similar to the last problem. In fact, we know we're going to have to do a divergence theorem. Let's think about our surfaces here. Square root of x squared plus y squared equals to z. That's a very famous surface. It's one we've kept seeing over and over again, and that's our cone. So we have our cone here, and that just keeps going up. 2 minus x squared plus y squared. Well, if I just had z equals x squared plus y squared, that's a surface we've seen for quite a long time. That's a bowl. Adding the minus, that flips the bowl upside down. Add the 2, that shifts the bowl up. So what you get is you get a bowl that starts here at 2 and then just sort of goes down. So a bowl here, really that's an elliptic paraboloid. And so we want to be above the cone, below the bowl. And so we look at this and we say, okay, so our shape is sort of this shape here, and we'll shade that in. It's kind of similar to sort of like an ice cream cone, and then there's a little bit of a nice big scoop on top that we're working on. Okay, so there's our shape. All right, well, now the question becomes, how do we describe the shape? Because we're going to have to figure this out. This isn't just something we can look at and say, aha, I know exactly what this thing is. The thing is that the top is not a sphere. And if it's not a sphere, generally speaking, spherical coordinates do not work very well. But you'll notice that there's a couple things here. One, there's a lot of this rotational symmetry. And whenever you have something with a lot of rotational symmetry, we should think cylindrical coordinates. The other thing that's sort of saying, hey, think cylindrical coordinates, is we consistently see an x squared plus y squared. When you keep seeing x squared plus y squared, that's the sign, switch to cylindrical, because in that setting, x squared plus y squared becomes r squared, and life becomes good. Life becomes wonderful. So, what do we have? Well, if we switch to cylindrical, then this expression here becomes r is less than or equal to z is less than or equal to 2 minus r squared. So for that, what we can do is we can look in what I like to call here the RZ plane. So I'm going to look for z going up and down, but r strictly positive. R equals z is this line. And then z equals 2 minus r squared. Well, that's our upside down parabola. So this is our z equals 2 minus r squared. So what's happening is that this is our region. Then if we just rotate that around, that's our shape that we get. Okay, so there's our shape, but what we haven't done yet, let's go back to our problem, is what are we going to do with our shape, our solid here? So we're going to use the divergence theorem. So we get that the integral on the surface f dot n d sigma, well, that's the triple integral over t of the divergence of f, which I can write as del dot f, and dv. So let's go ahead and compute the divergence. So come to our first term, take the derivative with respect to x. Arctangent goes away. Ah, arctangent, you're such a beautiful function, but not all the time. Sometimes we need to do other things. So 5 sine squared of z. Now don't panic. Wait until you get it all worked out. Maybe this sine squared of z will simplify. Go to the next term, take the derivative with respect to y. The log term goes away. And here you get 5 cosine squared of z. All right, and go to the last term, take the derivative with respect to z, and you get 7, because that term goes away. And then you have dv on the end. So what you end up with is, notice that this 5 plus 5 makes, well, this is 5 sine squared plus 5 cosine squared, which really makes this 5 plus 7 makes 12. You can even pull the 12 out. So what we have is we have the integral of over t of 12 dv. So really what we're after is 12 times the volume is the answer. And unfortunately, this shape, we don't know the volume of this shape off the top of our head. It's not a sphere or something where we're like, aha, I know how to find the volume of that. Which means we need to do more work. That's all right. That means that the integrals won't be too bad. All right, so we're going to with cylindrical coordinates. So let's set up our integral. So integral, 12. Then dv becomes r, dz, dr, d theta. Now theta, because we have symmetry all the way around, that goes 0 up to 2 pi. dr. Well, for that, what we have to do is figure out where is this intersection. So in other words, when does 2 minus r squared equal r? So I'm setting these two lines equal to each other. Now, we could just sort of hum and haw, or we could just say, oh look, I see a guess, r equals 1. And yeah, a guess is good enough if you check it. And okay, so there, see, I checked it. Boom, check. If you weren't sure, you could also move everything to one side and factor. So that tells us that r in this range is going between 0 and 1. Now, where does z go from? Well, we go from this bottom curve up until this top curve. So this bottom curve is the curve z equals r. And the top curve, that's the parabola, that's 2 minus r squared. All right. Now, we're going to have to do a little bit here. We can move the d theta, if you will, all the way over into here, because nothing else depends on theta. And then go from 0 to 2 pi d theta will be 2 pi. So I'll go ahead and put that out in front. And we already have the 12, so I'll combine the 2 pi with the 12 to give us 24 pi. Integral 0 to 1. Now, when we integrate this with respect to z, we're going to get rz. Remember, the 12 came out here. And we're going to evaluate z equals r to z equals 2 minus r squared. We'll do this dr. Yes? Yes. All right. So that gets us 24 pi. Whoops. Try that again. 24 pi integral 0 to 1, and that's r times 2 minus r squared minus r dr. So that is 24 pi integral 0 to 1 of 2r minus r cubed minus r squared. All right, well, let's work this out. So that would be 24 pi, and then when we integrate, well, term by term, r squared minus 1/4 r to the 4th minus 1/3 r cubed, and then evaluate 0 to 1. Well, the nice thing is, you plug in 0, you get 0. Plug in 1, what do you get? Well, 24 pi out in front, 1 minus 1/4 minus 1/3. Now, we could, of course, try to expand all these out, but or rather get a common denominator. Let's just multiply through. If you multiply through, what do you end up with? Well, you end up with 24 pi. Then we multiply it by 1/4. Well, that'll be 24 divided by 4 is 6, so minus 6 pi. Then divided by 3, that'll be 8 pi. So 24 pi minus 6 pi minus 8 pi will leave us with a grand total of 10 pi. That's it. There's our answer. Okay, nice. Now at this point you're probably thinking, cool, every problem we're ever going to see is a divergence problem. Well, maybe, or maybe not. So let's do an example. Let C be the parametric curve 2 sine t, 0, 2 cosine t, where 0 less than or equal to t less than or equal to 2 pi. So it's a curve. Now, automatically the divergence theorem is out. It cannot possibly work. How do we know that? Well, the reason we know that is because of the following. Because the divergence theorem talks about integrals of surfaces and solids. So it's 2-dimensional and 3-dimensional integrals. This is 1-dimensional, so divergence is definitely out. So here we go. There's our figure. And the question says, well, find the integral along this curve of this thing dot t ds. So we're integrating something along this curve. Now, what are our options? Well, one option, which right now seems to be our only option, is actually do the integral. However, one thing that we should sort of figure out is that we should probably never ever do the integral that's been asked. What we should do is say, well, what's our tool? Now, notice that this is not a curve in the plane, but it is a closed curve. In other words, I loop back on myself. So if I'm a closed curve, I can use Stokes' theorem. But you might say, there's no surface here. Aha! When there is no surface, that means we get to pick a surface. There's lots of surfaces you can pick, but the rule of thumb is always pick the easiest surface. And for us, the easiest surface would just be to fill it in. So we're going to take this surface here and fill it in. And if we do that, we get a nice disk. So now I can think of the curve as being a bounding bounding curve of a disk. All right. Well, that still leaves one other thing we have to figure out, which is, this is a nice, it's flat. We love flat things. Flat things are the best. They are wonderful. But you got to still ask the question, what's your orientation? So in other words, there are two sides to this disk. There I could come up from the positive y, or I could come from the negative y. Which side should I stand on? Now, if you're a believer in the right hand rule, which means you take your right hand and you use your fingers and you curl that around, that gives you an orientation. So if you can imagine that you have this, you're sticking it around, your thumb would point in the positive y direction. Well, that's actually the correct use of the right hand rule, where you think of the fingers as curling around in the direction of the curve. So it turns out that our normal is going to point in that direction. Now, if you're not sure, just imagine that you were a tiny little person that was walking along this curve. If I walk on this side, what happens? Well, as I'm walking along here along the edge, the region would be over here on my left-hand side. And remember the song, to the left, when you walk the curve, keep the region to your left. That's right. You're going to stay on the left. Whereas if you were on the opposite side, you would have your region on the right-hand side if you were to follow the direction, which that's not right. All right, so in particular, what can we say? Well, our normal vector, n, is actually really simple. It points only in the y direction. It has to have length 1, so it's 0, 1, 0. Okay, so let's call this surface here. We'll call it, by the way, we'll call it G as our surface. And it's a nice disk. So this is going to be the integral, double integral over our surface G of the curl, so del cross e to the x plus 2z, comma, x cubed z squared, comma, log of 1 plus z squared. And then we're going to do it take that, forgot the one piece, dot n, don't forget the dot n, dsa. All right, so that's this right here. This is Stokes. So that's where we're using Stokes' theorem. Now, that means we've got to actually do a curl. Okay, so let's do our curl. And, all right, so we have our I, j, k, partial x, partial y, partial z, our e to the x plus 2z, our x cubed z squared, and our log of 1 plus z squared. Now, we could save ourselves a lot of time and say, you know what, this n, it's not just anything, it's 0, 1, 0. Which tells us what? It tells us I only care about the middle entry. Because this curl is going to have 3 entries. The first, middle, last. It doesn't matter what the first entry is, doesn't matter what the last entry is, only matters what the middle entry is. Now, I won't do that, but you could do that and save yourself some work. Now, I so often do my determinant by going down. Let's do a cofactor expansion, just for fun. So how does cofactor expansion work? Well, so for example, we're going to go along the first row, and we cross out the first row and column, and we see that little 2 by 2 matrix. So that's going to be partial y, partial z of x cubed z squared, log of 1 plus z squared, and that's in the I direction, plus, now I come in here to j, and I cross out the row and the column, and I have these entries. Now I wrote the word plus, it's actually not a plus, my mistake, common mistake, it's really a minus, because there's an alternating sign, plus, minus, plus. Very common mistake. So that's all right. We caught it before we got too far along. So minus partial x, partial z, e to the x plus 2z, and log of 1 plus z squared. And that's in the j direction, plus, and again, plus, minus, plus, so we're okay. And again, you cross out that row and that column, you get a little 2 by 2 matrix left, and we want to take that 2 by 2. So partial x, partial y, you get e to the x plus 2z, and x cubed z squared. Okay, now, again, I could just say, oh, this looks like stuff in the I direction, something in the j, and stuff, and I'd be okay, because I recognize that these are not important. I'd still get the right answer. We'll go ahead and fill those in a second, but let's go ahead and finish the problem. Okay, so I need to figure out this middle entry. So let's figure out. So we're taking the derivative with respect to x of log of 1 plus z squared. Look, there's no x. That's 0. Boom, gone. Then we're going to subtract the derivative with respect to z of e to the x plus 2z. So that would be, this derivative would be 2. We're subtracting it, but there's another minus here, which makes this a 2. So this becomes something to something. We dot these together, and we see that, aha, this is the integral over our surface of 2 dsa. Now, what does that mean? Well, if you pull the 2 out, which you can, you get this, 2 integral over your surface of dsa. And what does that represent? Well, if you think about what's happening, integration says split things into small pieces, and then what's the contribution of each piece? The answer is it's that little bit of area. So I'm adding up all the little pieces of area, which means I'm finding the total area. So this is really 2 times the area of the surface. Well, let's look at our surface. It's a disk. How big is our disk? Well, notice the 2 here. See, our disk, this is a disk with radius 2. Well, that means that it's a circle with r equals 2 in 3-dimensional space. So that means the area will be pi times 2 squared. Our 4 pi times 2 more gives us 8 pi. And that is the answer. And we're done. Okay, I said I'll go back and finish this up. Okay, so that's using the knowledge ahead of time. Hey, I only need to pay attention to the middle entry. If we wanted to take the curl all the way, well, okay, derivative with respect to y of log of 1 plus z squared, 0. Derivative with respect to z of x cubed z squared, that would be 2x cubed z. The 2 stays the same. We haven't done anything. Change that. That's a good sign. All right. And, well, what's our last piece? Well, it's over here. And derivative with respect to x of x cubed z squared would be our 3x squared z squared. And there is no y in e to the x plus 2z, so that's nothing. And so that's our actual curl. Oh, nope, I made a mistake. Do you see it? I forgot. I messed the sign up because I need to subtract here. So there's a minus sign. There we go. Now that's the curl. All right. You always double check. It's good to double check. Now you might be wondering, how could you double check? Well, one way to double check is, remember, if you take the divergence of this, you should get 0. And if I hadn't had the minus sign, those terms wouldn't have canceled. They would have doubled up. But now the minus sign helps cancellation. So there's the actual curl, but again, it's sufficient for us just to know what the middle term is. All right. You'll see that this problem looks intimidating, but once you strip it down using the theorem, it actually becomes not so bad. And that's our goal. Our goal is not to make these problems bad. Our goal is to make these problems fun, because problems should be fun. It's always a nice time to play with things. Okay, next example. Let D be the solid with 1 less than or equal to x squared plus y squared less than or equal to 4, and 0 less than or equal to z less than or equal to 2. Look at the picture. Okay, I see the picture. In fact, we can even see exactly what it is. We don't even have to figure out how to draw. It's a cylinder where you've drilled out a smaller cylinder down the middle. Well, that's easy. In fact, already we can see that we're going to switch to cylindrical should the need arise. Only problem is learning how to spell the word cylindrical. Okay, there we go. All right. So should the need arise, this is perfectly set up to be cylindrical coordinates because we see cylinders. You should always think cylindrical when you see cylinders. Let S be the surface of D. Okay, so D is the solid, S is the surface, and N is the outward pointing normal to D. And find the following. And D sigma, again, that's just another way to say D of SA. We're integrating on our surface some function dot n d sigma, which means we have our outward pointing normals. Okay, so what's the tool? Well, we should see right away that our keyword here to work off of is solid. So this is divergence theorem. But the other thing we see is we're integrating on our surface f dot n. And so that says you're really finding the flux. So we're finding the flux through the surface. Now, if you think about the surface, there is one thing you might wonder and say, are we allowed to do this? And before we formally say what the question is, the answer is probably yes, we are allowed. But okay, what's the issue? Notice that this is not just any solid, it's essentially a solid with a hole. If anything, this is like a donut. You can think of it as a donut. And so we have like a holy solid, a solid with a hole. Does that affect our technique? And the answer is it has no effect at all. We're perfectly fine working with solids with holes. No issues, just proceed as normal. Okay, well with that out of the way, now we're ready to proceed as we might normally do. All right, so this will be, according to the divergence theorem, the integral over our solid D. And now we go through, we're doing the divergence here. So we're going to do the divergence of f dv, where f is this whole expression. So that's the integral over our solid D. And okay, go through term by term. And remember, we're going to take derivative with respect to x, derivative with respect to y, and derivative with respect to z. Come here, derivative with respect to x, that's minus 4x cubed. Go to the next term, derivative with respect to y is 4x cubed, but plus. Okay, that's a good thing. We like it when things cancel. The arctangent goes away. Come to the last term, and well, we're not going to get cancellation. We're going to take derivative with respect to z. That's good news. But there is something here. The reason I say it's good news is we don't have to deal with that. So we get 6z square root x squared plus y squared. And that's what we're going to integrate dv. All right, so we're going to have to integrate because this is not just a simple, haha, look how easy this thing is. So let's talk about our shape. Now, first thing is we're going all the way around. So we have that nice full symmetry. That tells us that theta is going to go between 0 and 2 pi. R, well, think about the picture. Really think about what's happening down here in the plane. What do you see? Well, what you see is you see an annulus, which essentially means a big circle with a little circle popped out. And what we have is we're going between a circle radius 1 and a circle radius 2, because this is like r squared. So r goes between 1 and 2. And where does z go from? Well, it goes from 0 to 2. Now you might say, how did you know that? Well, because it said it right there. Ah, that's a good technique. See what it says. So this is going to become integral, integral, integral. We rewrite this in terms of our new coordinate system. The z stays z. Square root of x squared plus y squared becomes r. So 6z r. Then we do our dv. Well, dv is r dz dr d theta. Theta goes 0 to 2 pi. R goes 1 to 2. And z goes 0 to 2. Now, what do we need to do? Well, we just need to do this integral. This is an integral which you can break up nicely. So we're going to do that. We're going to break this integral up nicely. So let's see, how can we break it up? Well, 0 to 2 pi d theta. That's an easy integral. 1 to 2 of r squared. That's easy integral. And then we have integral 0 to 2 of z. Also easy. And then we have a 6. Well, I can put the 6 anywhere. But I see, oh, you know what would be good is if we had a 3 here. So I'll go ahead and put 3 here. And then what would be good if I had 2 there. Okay, I'll put 2 there. And 3 and 2 together make 6. Now, if you didn't see that, it doesn't matter. It would all work out in the end. So this first integral, easy enough, 2 pi. The second integral, that's r cubed from 1 to 2. Well, you take 8, subtract 1, and you get 7. Here you're going to get z squared from 0 to 2, which becomes 4, subtract 0, which is 4. So you get 4 times 7 times 2 pi, which would give you 56 pi. And we're done. Nice. These are great problems. Do we really have to stop? Can't we just keep going all semester? Can we have like a calculus 4? Well, probably not. We got to stop at some point. Okay. Let D be the solid where x, y, and z are greater than or equal to 0, y is less than or equal to 1, x plus z is less than or equal to 1, and z is less than or equal to 1 minus y squared. And they even gave us a picture. It looks like something you definitely wouldn't want to step on because that does not look comfortable to step on. And we're going to have S as the surface of D. And we're going to find the following. Something that looks terrible. But remember, looks can be deceiving. Just because it looks bad doesn't mean it is bad. And it says, simplify as much as possible. Now, what does that mean? It means the answer better be really simple. And probably, if we get to the end, and the answer is not really simple, we probably need to do something else. Oh, okay. But let's see where we get to in the end. And then we'll decide whether or not we need to do something else. All right. So, well, let's begin. So what's our technique? Our technique, we see the word solid, we know we're thinking divergence. So let's do divergence here. So we're going to do our triple integral over d of our divergence. So this looks like a terrible expression, but remember, looks can be deceiving. Don't be intimidated. Just go through term by term. Derivative with respect to x, well, the first term, 20. Come to the next term, derivative with respect to y, there's just one right there, 10 cosine squared x. Come to the last term, derivative with respect to z is 10 sine squared x. Now one of the things you might notice here is that on some problems we have I, j, and k. Other problems we have our angled brackets. You should be comfortable doing either because it just depends on which problem that you have, on which one you'll use. It's just different notation. Notation should not be the thing that stops you. It should be, you're asking what should stop you. Well, nothing should stop you. You should be unstoppable. By this point, you're amazing. And don't let anybody say that you're not. Well, again, cosine squared and sine squared becomes 1. 20 plus 10 becomes 30. So, this is just integrating 30 dv, which means we just need to take the volume of this shape, multiply by 30, and life is good. But it's not so clear. What is the volume of that shape? Well, let's find out. Looking at this, we say, okay, what are we going to need to do? Well, we're going to need to set up an integral. This is not going to be spherical coordinates. No spheres are involved. It's not going to be cylindrical. There's no rotational aspect going on. And so we really are going to set up an integral, in Cartesian. And for that, we want to know the order of integration. Well, they gave us a hint. They said, hey, hint. Here's a really nice order of integration. dx, dz, dy. Well, let's not ignore their hint. Let us embrace their hint. They gave us a hint. Let us use their wisdom. Okay, so we're going to try to understand this shape. Now, when you look at this shape, there's a couple of bounding surfaces. Some of them are easy to spot. So what are the ones that are easy to spot? Well, you have the plane. So for example, this bottom part, this is the plane z equals 0. This back side, that would be the plane x equals 0. And this other side over here, that would be the plane y equals 0. Okay, so those are three of your surfaces that are bounding it. Now you can look and see, all right, what are your other things to look for? Well, notice you have these equations, x plus z equals 1, z equals 1 minus y squared. Well, x plus z equals 1 would be in the xz plane. That would be a line. So this flat surface here, it's not so clear that it's flat, but in fact it is a flat surface. This surface is x plus z equals 1. Now this other one, we look at it, we say, oh, that's like a YZ plane, see, because there's only Z and Y. And it would look like a parabola. Well, that looks like it could be a parabola. In fact, it is a part of a parabola. And then it just copies down, so it's sort of like this ramp here, maybe like a skateboard ramp. So that surface is the surface Z equals 1 minus Y squared. Okay, so there are our planes. Now we're going to set up our integral following the hint in the order dx, dz, dy. So this is going to be integral, 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 30 dx, dz, dy. Well, that says look down the x-axis, and when you look down the x-axis, what you see is the yz plane. And in particular, what you really see is that curve there. Z equals 1 minus y squared. So there's 1 over here. Actually hits that 1 here. Okay. Well, where does y go from? 0 to 1. Okay. So 0 to 1. Where does z go from? Well, that's going up and down. So it's going here from z equals 0 to z equals 1 minus y squared. 0 to 1 minus y squared. Now, where does x go from? Well, x, go back to your three-dimensional picture. You want to move parallel to the x-axis. So what's going to happen is I'm going to start back here on this back face, which is the x equals 0, and I'm going to move parallel to the x-axis until I hit this front face, which is x plus z equals 1, which we need to solve for x. That's 1 minus z. So I'm going to go 0 to 1 minus z. All right, now we're ready to go. So we're just going to work our way through one layer at a time. 0 to 1, 0 to 1 minus y squared of 30x. Evaluate x equals 0 to x equals 1 minus z. And then we have a dz dy. Okay, so this is integral 0 to 1, integral 0 to 1 minus y squared of 30 times 1 minus z. Okay, all right, sure, we can do that. dz dy. Well, let's integrate. So that's 30. Then here I'll have z minus 1/2 z squared. Then I'm going to evaluate z equals 0 to z equals 1 minus y squared dy. So let's plug these in. Now we plug in 0, you're going to get 0. That's good news for us. Plug in 1 minus y squared. Well, you're going to get 30 times 1 minus y squared. So 30 times 1 minus y squared. Now here, 30 times minus 1/2 makes minus 15. Then you're going to get z squared, which is already 1 minus y squared. So you get 1 minus y squared squared, which is 1 minus y to the 4th. All right. Now, at this point, you're like, look at this terrible thing you have to integrate. But you can actually do it pretty simply. Now, one way you could do it is you could do it by substitution if you let u equal 1 minus y, which, let's go ahead and just do that. U equals 1 minus y. What do you get? Well, you get du is minus dy. And so this becomes the integral from 1 to 0. But because of this minus, there's a minus in front. And then you get 30u squared minus 15u to the 4th du. Well, just flip the bounds, get rid of the minus. 0 to 1, 30u squared minus 15u to the 4th. Okay, well now it's not so bad. So what's the integral of 30u squared? Well, the answer is it's 10u cubed. The integral of 15u to the 4th, Well, that would be u to the 5th, but divided by 5. So minus 3 u to the 5th. And evaluate 0 to 1. If you plug in 0, you get 0. Plug in 1, you get 10 minus 3, also known as 7. And there's our answer. Well, no wonder they wanted us to simplify as much as possible, because the answer was very nice. In fact, this problem came from an old exam. Fun note, it was problem 7 on the exam. That's how people were like, whoa. Some people didn't realize that until a year later, and they're like, whoa, problem 7. The answer was 7. Trippy. You never know. You never know. Who knows? Okay. Let's do another problem. Suppose f is our vector field minus 2yi plus 2xj plus xy plus z squared k, and s is the surface x squared plus y squared plus z squared equals 9 with z greater than or equal to 0. What is that? Well, notice it's an equal 9, not a less than or equal to 9, which means it's just the shell of the sphere with z greater than or equal to 0. So what you have is you have the following. So S is a sphere of radius 3, but you cut it in half. Okay, so here is S, and by the way, it says N is the upward pointing unit normals. So our normals point in the positive direction. So upward pointing just means that the Z component is positive. So there's our surface S, and be observant and say, oh, this is a surface which has an edge. So this is our boundary of S is a circle. So that might be helpful. Whoops, circle. There we go. Okay. All right, now what can we do? Well, it says find the integral of del cross f dot n d sigma. Again, remember d sigma is just another way of saying dsa. Well, what's the right technique? This is definitely not divergence, not a solid, but there's a couple of clues here. First off is the fact that you have a surface with a boundary, but here, I think a pretty big clue is the fact that you see this. The fact that you see a curl. So when you see a curl, that says, oh, Stokes theorem, that's perfect for this kind of problem, because this is a Stokes theorem type problem. It absolutely is. Okay, so since it's like a Stokes theorem type problem, we should be thinking of applying Stokes theorem. So we say, okay, how do we apply Stokes theorem? Well, there's a couple of options. One is do the integral they gave you. Almost never do we choose that option. It's not that it doesn't work, but the reason we almost never do that is because that's probably the hardest way to do the problem. What we want to do is not work hard, we want to work smart. Okay, so how do we work smart? Well, two options. One is to say by Stokes theorem, we can say, all right, this is the same as the integral along the boundary of S of f dot t ds. Oops, sorry. Okay, so that's option number 1. And, sorry, that's option number 2. First option being do the integral they gave you. Not going to do that. Now, there is one more option, which is to say, you know what? Let's not do the integral on our surface that they gave us. Let's do our surface integral on, say, a new surface. I'll call it G for surface, right? G for Gurfus, del cross f dot n d sigma. Now, the question is, what should G be? Well, the answer is make G just be any surface which has the same boundary. Now, because this bounding curve is flat, what we can do is we can say, oh, let's just make our new surface something which is flat. So it's like we're taking this and we're taking this bump here and we're sort of going to push it flat. Whoosh, push it in, push it in. An uncomfortable analogy might be if you've ever had like a blister, and you had to like pop it, push it flat. Okay, like I said, that's an uncomfortable analogy. So our boundary is a circle. So what we can have is we can have our G can just be our disk, flat disk here in the xy plane. Now, if we make that our bounding surface, our new surface G, the question becomes, what happens to our normals? Well, our normals, notice that they're pointing up. And as you push it flat, the normals are going to stay moving in, and they're still going to point up. So our normal would become 0, 0, 1. Pointing up in the positive z direction. And so this is our G. Okay, so let's suppose we chose this option. Let's see where that takes us. Well, we'd have to do del cross F. So let's do that. And notice, what do we need? Well, we just need to know the last entry. So del cross F, that's our I, J, K, partial x, partial y, partial z, minus 2y, plus 2x, xy plus z squared. All right, so we take our ijk and we just start going, Now, I'm just going to go ahead and speed things up and say, look, I don't care what that is, I don't care what that is, because they're not going to matter. That 0 says, ignore them. They don't matter. What does matter? What's attached to the k? So k has what? Partial x of 2x, so that would be plus 2, and then subtract partial y of negative 2y, so it would be 2 plus 2, aka 4. So there's 2 entries, and then there's a 4. And you can, at your leisure, figure out what those other 2 entries are. They are not going to be that interesting and not going to contribute to the solution. All right, so what do we have? Well, our integral becomes the integral along G of something 4 dot 0, 0, 1 d sigma, which becomes the integral along G of 4 d sigma, or if you like, the 4 comes out, integral along G of d sigma, but as we've mentioned before, that's just the area of the surface. So 4 times the area of G. Now, what is the area? Well, it's a circle. Which circle? Radius has to be 3. So circle radius 3, that says the area of this would be pi r squared, 3 squared, which means we'll end up with 36 pi. Done. Done. Now, if you're going to do this, make sure you indicate it's something and not just that you're being lazy. Let's see if what would happen if we did it this other direction here. Okay, suppose we did want to go ahead and do this direct way. You know, what Stokes' theorem actually says. Well, if we wanted to do that, what we'd have to do is we'd have to come into the plane and we'd have to find a good orientation. So the bounding curve here is going to go counterclockwise because our orientation points up. It's the curve that's bounding a circle, so I need a circle radius 3. So a curve that does that would be 3 cosine t, 3 sine t, and 0. Okay, because there's no z component. And cosine and sine, that's our default circle. The 3 makes it a radius 3 circle. So the other thing to note is that this is for time going from 0 to 2 pi, because that's how long it takes to go around a full circle. So this becomes the integral 0 to 2 pi. Now f dot t says what? Well, this is really the same as f dot dr. So it would be minus 2y. Well, okay, let me say that f dot t ds. This is again dr. So this would become the integral along boundary of S of minus 2y dx plus 2x dy, and then plus xy plus z squared dz. Okay? Minus 2i, 2x, xy plus z squared. Now, notice that z is 0. So what happens is when we integrate 0 to 2 pi, a lot of this simplifies. So you have minus 2 times y. So that's minus 2 times 3 sine t times the derivative of x. Well, the derivative of 3 cosine t would be minus 3 sine t. Plus 2x, so plus 2 times 3 cosine t times the derivative of y, which is 3 cosine t, plus something, something, something times derivative of 0, which is 0. And that is what we're going to integrate dt. Well, our first term, the minus minus, that's good, sine, that simplifies. So what do we end up with? Well, we are going to end up with 18 sine squared t. Here we're going to end up with 18 cosine squared t. And if you add those together, you say, that's just 0 to 2 pi of 18. Well, that's 18t from 0 to 2 pi. And 18 times 2 pi gives us 36 pi, which is the same answer. Now, which is the right way to do it? They're both the right ways to do it. Which one should you do? The answer is, which one do you feel comfortable doing? We're not trying to force you to go a certain route. We're trying to have, hey, do what's correct. And there's oftentimes more than one correct way to do it. And as long as you get the right answer, life is good. Life is beautiful. All right. So, let's try another problem. Given that f equals x squared I minus 2xyj plus yzk, and c is the intersection of the cylinder x squared plus y squared equals 1, and the plane x plus z equals 1, oriented counterclockwise as viewed from above, compute the integral along the curve of f dot t ds. Now, there's a couple of things to spot here. First off, this is a closed integral along a curve. It's not going to be divergence theorem because divergence theorem doesn't work with one-dimensional integrals. This curve is in three-dimensional space, and we're doing f dot t. So these are clues here. And so the clue is we're thinking Stokes theorem. Okay, so that's our idea. We're thinking this is a Stokes theorem problem. Let's see if we can figure out what's going on here. So it says, start with this cylinder x squared plus y squared equals 1. Now remember that in three-dimensional space, x squared plus y squared equals 1 is not a circle, but it's a cylinder. In other words, you just sort of take this shape and copy it up and down. So we have this, okay? So here's our cylinder sitting here in three-dimensional space. All right? And then we have this line, x plus z equals 1. But it's not a line. It's a plane, even though there's no y. Well, what does x plus z equal 1 look like? Well, what it looks like is it's going to intersect the x-axis at 0 and the z-axis at 1. And other than that, it's going to not do anything else. So what we have is we have this sort of plane that's slicing down here. So I have this plane coming in at like a 45-degree angle. And what's going to happen is that there's going to be an intersection. In fact, they intersect at that point right there, where you have the point 1, 0, 0. And then this will wrap around, moving up, intersects on the backside, and then it comes back down. So what you have is you actually have, essentially it's an ellipse that's been tilted. So this is our curve C. And moreover, it says it's been oriented so it's counterclockwise as viewed from above. So that's actually a good orientation. Counterclockwise viewed from above is sort of the one that we normally would go with. Now, probably we are not meant to do this integral in the way the problem has told us. And the reason that we're probably not meant to do that is we'd have to come up with some sort of a parameterization. it's not terribly hard to come up with a parameterization, but it's not very fun because you have to sort of figure out, all right, well, what's going on? The parameterization is because you're on a circle, it would be cosine t sine t, that would be your xy. And the cosine t sine t is the correct way to go counterclockwise in your view from above. How do you get z? Well, z is 1 minus x, see, because you're on that plane x plus z equals 1. So your z component would be 1 minus cosine t, and then you have 0 less than or equal to t less than or equal to 2 pi. So if you were to go for c, there's your parameterization. But again, it does not look very inviting. We see things like, an x squared. That could be tricky. We don't want it to be hard. We want things to be easy. So we start thinking, okay, suppose we were to do Stokes' theorem. I have a closed curve. What I don't have is I don't have a surface. So we say, all right, let's just fix that. I just have to come up with some nice surface here that fits in. Well, the surface should be something preferably flat. So we say, okay, well, let's make this a flat surface. So let's just put in this surface here. And you might say, well, what's the surface? Well, the answer is they actually gave it to us. It's this x plus z equals 1. That's our surface that we're going to be working with. All right, so now we have our surface. Cool. And what about the orientation? Where's the normal vector? Well, because this is counterclockwise, that's going to be pointing up in an, I'll say, upward pointing normal. Okay, so let's call our surface, for a second we'll call it G. And we're going to come back and talk more about this in a minute. So, according to the theory, what do we have? Well, the integral along our curve of f dot t ds is equal to the integral on our surface G of the curl of f dot n dsa. Nice. Okay, so we've got something to start with. Now we have something we can play with. So we've got to find the curl of f. So we're actually going to go ahead and find the whole thing because it's not so clear what's happening here. So let's just work through this. So let's do the curl of f. So I, j, k, partial x, partial y, partial z, x squared minus 2xy, and yz. Now, if we do that, what do we get? Well, we get, in the I direction, the derivative with respect to y of yz, which would be z. So that's zi. In the j, partial z of x squared, nothing. Aha, 0j, because there's no z there. K, partial x of minus 2xy. Well, the derivative with respect to x of minus 2xy is minus 2y. K. Now, I was going in the downhill. Let's start going uphill. Derivative with respect to y of x squared? 0. So there's a 0k there. And then, derivative with respect to z of minus 2xy? Well, 0. There's no z. So that's with the I. So there's a minus 0i. I did put a plus 0k. It should have been a minus 0k, but thankfully 0 is very forgiving. The last part, derivative with respect to x of yz, well, there's no x. And therefore, we're going to get 0. So that's going to be 0j. Well, that's, wow, that was actually amazingly nice. Okay, so what do we end up with? Well, we ended up with z, comma, 0, comma, negative 2y. All right, so that's our curl. So this is the integral on our surface G of z0 minus 2y dot n dsa. Now at this point you're probably thinking, okay, but how do you actually integrate that? And here's the cool thing, is I can think of this as the following way. I can say, aha, I can think of this as the flux of z0 negative 2y through g. Now you might say, well, wait a second, is that what we're doing? And the answer is yes. That is exactly what we're doing. Whenever you have some f dot n on a surface, you're doing a flux. So you're allowed to think of a flux that way. Now, what do we have? Well, G isn't just any surface. It's a surface, if I solve for this, it's z equals 1 minus x. And now, you might say, okay, well, why is that helpful? Well, if you're doing flux, remember you have the following. This is equal to the integral over r of minus m f sub x minus n f sub y plus p dA. So, we might say, I remember something vaguely like that, but okay, well, let's do a quick review. F here is referring to the function. So in this case, our 1 minus x is our f of xy. M and p is our vector field. What is r? Come back to our picture here. R says, what is this surface over? So imagine looking from above. Well, we don't have to imagine too hard. The answer is what our surface is over is it's over a circle of radius 1. So r is a circle of radius 1, x squared plus y squared less than or equal to 1. So let's apply that here. So applying that here, we'll get the following. This is equal to the integral over r of minus m. Now you might say, aha, z is bad. Well, but you can replace it by 1 minus x. So minus m, which becomes 1 minus x, times f sub x. So then multiply this by the derivative of the function with respect to x, becomes minus 1. Minus n, which is 0, times f sub y, which is 0, so minus 0. Then plus p. So plus p will be plus a minus 2y. And that's dA. This becomes the integral over our region of, and if you put this multiplied out, you'll get 1 minus x minus 2y dA. Now at this point we could work this out, but I think we've been doing this for quite a while. Let's just go ahead and cut to the chase. There are 3 pieces here. One of the pieces is really easy. First off, let's talk about the integral of 1. If I integrate 1 dA, what do I get? The answer is I get the area of the region. What's the area of the region? It's pi. Okay, that's nice. What happens if I integrate x? Well, if you integrate x, what happens is you're going to get cancellation, because the region has that symmetry. And what you're doing is, if I look at a piece here versus a piece flipped across, I'm going to get the opposite value. So they're going to cancel out. So that's going to go to 0. How about minus 2y? Similar idea. There's symmetry again. If I flip across this way, I again get cancellation. So that's going to give me 0. And therefore, final answer is pi. And we're done. Nice, nice. Now there are other ways you could have done this. You could have actually explicitly computed dot n and then had a hard time. But if you remember that you have this notion of flux, that saves the day. It helps you get through it. All right. Well, let's try another one. Consider the open trough, and it's G, formed by taking the surface of the solid, formed from the cylinder with x squared plus z squared less than or equal to 4, and 0 less than or equal to y less than or equal to 3, then taking the part of the surface with z less than or equal to 0. Okay, that's a very long way to explain our shape. Let's see if we can figure out what that's saying. So x squared plus z squared equals 4. That would say, if I were to think of that, if I have my x, y, z, I really think of that as a circle here in the xz plane. So I have my circle here in the xz plane. And now I'm going to have 0 less than or equal to y less than or equal to 3. So it's like I'm copying this here. And so I have this copied down to where I have 0 less than or equal to y less than or equal to 3. So that's sort of our shape, if you will. Okay, that's our surface of our cylinder. But then it says, wait, take the part of the surface with z less than or equal to 0. So it's like we're cutting it, and we're only keeping the part that's below. So what we end up with is we end up with something that looks kind of like the following. We have this top part here, and then there's this bottom. All right, so there we go. Now, in particular, we should really be thinking this as not just a surface. This is really a surface with an edge. So this is the edge of the surface. And then what we can do is, the reason we call it a trough is you could now fill this part up here with something. I don't know, maybe you could put some water or something inside of here, so you have this sort of thing here. But remember, it's not a solid, it's just the surface, Okay, so there we go. All right. So we now have our shape. Find the integral on the boundary of this shape. So here's our integral of xy minus z plus x to the 7th, comma, 29y minus x squared plus zy, comma, y minus xz dot t ds, where the boundary is oriented counterclockwise when viewed from above. Okay, so that means I have this nice counterclockwise motion. Now, we say to ourselves, okay, we are probably not going to do the integral that they gave us. Why? Because we have yet to do that today. And we've been at it for quite a while. At least it feels like it. Okay, so we're not going to do that. So what are we going to do? Well, we're going to use our theory and say, all right, well, this is a problem which is set up for Stokes. And why is it set up for Stokes? We have an integral on a closed curve in three-dimensional space. Perfect for Stokes' theorem. All right. So, what does Stokes' theorem say? This says that it'll be the integral along our surface G of del cross f, the curl of f, dot n dsa. Now, we look at this and say, okay, this is promising, but doing that, we'd have three pieces of surface. You have this little half circle here, you have another half circle back there, and you have the side of a cylinder. And we say, well, no. That's the wrong thing to do. What's the right thing to do? Well, the right thing to do is to say, let us choose a better surface. So we say, all right, well, what do we need? We need to make sure we still have the same boundary. So what do we have? Well, our boundary looks a lot like a rectangle. In fact, it's a rectangle sitting here in the plane. Notice that we're going from positive 2 to negative 2 here in the x direction, and from 0 to 3 in the y direction. So we need to find some surface which has that rectangle and is easy to work with. And the answer is just put in the flat thing. The flat thing is the best thing. So we're going to go with that surface. And we got to be consistent with the orientation. So the orientation currently is going around in a nice counterclockwise. And so the right direction would be the normal vector of 0, 0, 1. We need to be standing up. You can imagine, of course, that you're standing on this surface, and that as you walk around, if you walk around here, your region is always to your left, to your left. When you walk the curve, keep that region to your left. Good. Now, why is it 0, 0, 1? Well, I have to point in the positive z direction, and a normal vector is always a unit vector, so that's why it has to have a 1 on the end. So let's call this surface, we'll call it h. So really, this is the integral of h of del cross f dot, and now I'll go ahead and put in the 0, 0, 1. 0, 0, 1 dSA. Well, that tells me when I'm computing this curl, I really only care about that last entry. Okay, so let's compute our curl. So, del cross our function xy minus z plus x to the 7th, comma, 29y minus x squared plus zy, comma, y minus xz. So we have our I, j, k, partial x, partial y, partial z, and write it down yet again. All right. Now, you should be very suspicious and be like, I think, z times y, sorry, and I think nice things are going to happen. So, what's going to happen is we're going to get stuff, because we don't care about those pieces, comma, we do care about our last piece. So, what happens? Well, we have k partial x of 29y minus x squared plus zy. The only place where x shows up is right there. Get rid of that is minus 2x. And then we have the other term will be partial y of xy minus z plus x to the 7th. Well, when we take the derivative with respect to y, what happens? Well, x to the 7th, z go away. You're left with an x, and we're subtracting. So minus x. All right. Well, what does that tell us? Well, that tells us that we have something minus 3x. So, what we end up with here is we end up with the integral over h, something minus 3x dot 0, 0, 1 dSA, which is integral over h of negative 3x. Now, we come here and we ask ourselves the question, well, what is the integral of negative 3x? Well, the answer is if you think about our shape here in the xy plane, y goes from 0 to 3, but x is going from negative 2 to positive 2, which means that if I look at the contribution there versus the contribution there, they cancel out. And therefore, we're going to end up with 0. Okay, well, that's kind of sad. It's, you don't want to end up with 0. You want to end up with something interesting, but, sometimes 0 happens. And you just accept it. Accept it and move on. That is kind of an unfortunate thing. I was hoping for something more fun. Right? Yeah, well, if we end up with minus 3y, that would be more fun because we don't have our symmetry. But it is symmetric with respect to x. Because when we have a positive x, we have a negative x. So, all right. Well, c'est la vie, Such is life. Such is life. Well, one more. One last problem to finish it all. Our final problem for the semester. Let G be the surface consisting of the two parts r equals 1 for 0 less than or equal to z less than or equal to 2, and x squared plus y squared is less than or equal to 1 for z equals 0. Now, it even tells us what this is. This is the sides and bottom of a cylinder, like a drinking glass set on the xy plane. So what we have is we have this top circle here, and it goes down, and then we have this bottom part here. And what do we include? Well, we're going to include the bottom. Whoops. Shh, quiet. We're going to include the bottom, and we're going to include the sides. But we're not going to include the top. So the top is not part of our surface. Now, we have the following. Let n consist of the normal vectors which would point out. So that tells us what? Well, on the sides we point out, and on the bottom we're pointing down. So the question becomes, determine the integral along the surface of the curl dot n. Okay, so here's our problem. We've got to find this integral. There's a couple of keys. The curl. When you see something that involves curl, we think Stokes. There's something else. We have this surface, and that surface has a boundary. When you have a surface with a boundary, you think Stokes. So that's a double Stokes. All right, now what can we do? Well, one thing we could do is we could definitely do the integral as given. Probably the wrong thing, because we've learned there are better ways. Okay, so let's not do the integral as given. Another thing we could do is we could say, hey, we could figure out, let's do just the integral on the boundary. All right, true, you could do that. And it's not impossible. But there should hopefully be another idea, which is to say, let's just take this cup, and like it's something that you can smash. And we're going to push the bottom up. So if you push the bottom up, you still keep the same curve up on the top. So it's still a circle of radius 1, but this is now at height z equals 2. And so what you have is you just have this curve here. What's your surface? Well, your surface, you've pushed it up into it, so your surface is just the disk. What's your n? The answer is that n is the normal vector. See this normal vector down here? It's pointing down. As you push this up in, it's always going to be consistent. So it's like always pointing down, so that at the end, it's still going to be pointing down. So our normal vector would be 0, 0, minus 1, because it's downward pointing. So let's call this surface H. So what we get is that this is equal to the integral over H of this curl of this expression, yz, z squared, x squared plus xy, dot 0, 0, minus 1 dsa. Okay, so now let's take some time and we'll do the curl. Well, we're not going to take much time because, look, these first two components are going to be 0 automatically. So what we'll get is that our curl, we only need to focus on our last component, the k entry. So we set up our 3 by 3, partial partial x, partial partial y, partial z, and then we have yz, z squared, x squared plus xy. Okay, so there's our setup, and we're going to end up with something, because those aren't going to matter, comma. Now we come to the last part. Okay, so here we go for k. Partial partial x of z squared, nothing, 0. Then we're going to subtract, going this way, partial partial y of yz. So subtract, and here, take that derivative, we're going to get z. So this becomes the integral along h of 0, 0, negative z dot 0, 0, negative 1 dsa. Well, if you multiply that dot product out, sorry, not 0, 0, stuff, excuse me, I shouldn't have said 0, stuff, negative z, 0, 0, negative 1. If you do that out, that becomes the integral along h of z. Now here you say, well, what's true about z? This is the surface where z equals 2. So this is really the integral along our surface of 2. Oh, well, you pull the 2 out, and what you get is that this is 2 times the area of h, because you're just integrating dsa. And now you say, well, h, that's actually pretty simple. See, that's a circle of radius 1 we pushed up in. So it's a circle of radius 1. See, r equals 1. So the area of a circle of radius 1 is pi. So we get 2 pi. And that's our answer. Done. And we really are done. That was our last problem. Wow. Well, we've been together a long time now. Thanks for getting it through to the end. Not just for today, but for all the lectures. You know, we've been here a long time. I really hope you do well, and I really hope that you've learned. And I suspect if you come all the way to the end, it's been helpful. Good luck. I wish you the best, and many happy days of problem solving ahead. Bye.